All right, so before we dive too deep into the details of physical chemistry, maybe you're curious to know what it is that we're going to learn. What is physical chemistry? What are the topics in this field, and what delineates physical chemistry as apart from some other type of chemistry? So one way to answer that question is to list the various subdisciplines of chemistry. Physical chemistry, of course, is a subdiscipline of chemistry as a whole. There's a number of different subdisciplines of chemistry. We can list a few of those: analytical chemistry, biochemistry, inorganic and organic chemistry, in addition to physical chemistry. So that's a fairly common way of breaking up the topics in chemistry. That's not unique. That's not the only way to break things up. You might want to talk about materials chemistry. There's other subdisciplines of chemistry that you can consider as well. But that's a fairly common way of breaking up the topics in chemistry. Many of these you probably already have a reasonable understanding of what topics fall in these different areas of chemistry. Maybe you've had an organic chemistry course, or you know something about organic chemistry. Organic chemistry is everything to do with carbon, right? So carbon-containing molecules, the synthesis and properties of carbon-containing molecules, as opposed to inorganic chemistry, which is everything else, synthesis and properties of non-carbon-containing molecules. So that feels like it's already divided up all of chemistry into the carbon-containing stuff and the non-carbon-containing stuff, but that's just the molecules themselves. A field like analytical chemistry, for example, again, maybe you know because you've had some coursework, or maybe you can just tell from this word or from the name, analytical chemistry is not interested so much in the properties of the molecules themselves, but in the analysis, the actual act of doing the measurements and the analysis of those molecules. So that's interested in doing the measurements themselves, and therefore, since we often use instruments to do those measurements, the construction and the principles behind those instruments that we use to do the measurements. Biochemistry, of course, is interested in reactions and molecules that are biomolecules, molecules in living organisms. So not biology, not the living organisms themselves, but the chemistry that takes place in those living organisms. So again, those are reasonably clear from your prior coursework or from the words themselves. If you're like many students, you're a little more fuzzy about the boundaries of physical chemistry. What makes something a topic in physical chemistry? So that's the question we have to answer. The name, if we look at the name, physical chemistry makes it sound like it's got something to do with physics, right, or something to do with physical processes of some sort, and that's in the right direction. We can get some insight into the thing that makes physical chemistry by considering the various topics that are typically studied in a physical chemistry course. So in a typical PChem course, it's divided into several different subtopics: gas laws, thermodynamics, kinetics, quantum mechanics, and statistical mechanics. Again, that's not an exclusive list. Many people might want to add some more topics to that list or subdivide them further. But that's a reasonable list of the topics, the fairly broad topics that we'll cover within a physical chemistry course. Some of those are familiar to you already, most likely. Some of them are less so. I'll give you just an equation for each one of these to remind you or to give you a hint about. I should use a lowercase n for moles of gas. P equals nRT. You're most likely used to seeing that equation with a lowercase n for moles. So gas law is like the ideal gas law, P equals nRT. Thermodynamics involves relationships between different thermodynamic variables. One that you're likely familiar with is delta G is delta H minus T delta S. Kinetics is equations that describe, for example, how quickly some molecule or some concentration of molecules is appearing or disappearing. So the rate of appearance or disappearance of some species describes the kinetics of that species. Quantum mechanics you're likely less familiar with at this point if you're taking a physical chemistry course for the first time, but you've probably at least heard of Schrödinger's equation, which is a quantum mechanical equation. We'll talk a lot more about that equation. We'll talk a lot more about all these topics as this course goes on. Statistical mechanics, again, you're likely not as familiar with as some of the others, but here's an example of a very important statistical mechanics equation that we'll spend a lot of time talking about. And again, don't worry about these equations right now. My purpose is not to introduce or teach these equations to you. I'm just giving you examples of the types of things that you'd run across in the thermodynamics section of a course or in the kinetics section of the course and so on. And so having listed those topics, that's actually gives us a pretty good idea of how to describe the field of physical chemistry in general. What is it that gas laws and thermo and kinetics and quantum mechanics all have to do with one another that make them PChem topics as opposed to biochemistry topics or analytical chemistry topics? And the key is really the best illustration of each of these topics I could have given you was an equation to tell you this is the type of thing we're talking about. Any topic in physical chemistry, there's going to be a collection of equations that represent those particular topics. That's not true about organic chemistry. It's not true about all the areas of analytical chemistry. Analytical chemistry certainly uses equations, but not necessarily for all the pieces of analytical chemistry. You won't go very far in PChem without bumping into an equation of some sort. So the key is what physical chemists do is they like to understand and predict how systems behave by using some sort of model. That model might be a mathematical equation. It might be a physical model of some sort. It might be a graphical model, a cartoon that I'll sketch on the board, but we use models to try to understand physical systems and chemical systems. So what I just said is we like to understand and predict how chemical systems behave using models. So the key word here is models. Over and over in physical chemistry, we'll introduce some model for how the system behaves, often in the form of an equation, and then we'll see what that model tells us about how a system behaves. Physical chemists are agnostic. We don't care about whether we're making predictions about how a carbon-containing molecule behaves or a non-carbon-containing molecule or a biomolecule. We're happy if we can understand and predict how things work using our models. So that's one way of saying if you run into a new area of chemistry and you wonder, is that a physical chemistry topic or a biochemistry topic or whatever, if it involves a model and predicting what's going on, chances are physical chemists lay at least some claim to that topic. And again, this is not necessarily a super sharp division between different fields. Certainly many other fields of chemistry like to understand and predict what's happening. Many of them use equations or use models. There's, equations show up in biochemistry and in analytical chemistry and so on. So the boundaries between these fields are not always as sharp as I might be pretending they are. One last comment about this name, physical chemistry. Again, physical chemistry sounds a little bit like it's has something to do with physics. So if I say all of these topics that I've just described, those are all subdisciplines of chemistry. There's other scientific fields as well. There's physics, there's chemistry, there's biology. We've subdivided chemistry into different subfields and then physical chemistry into subtopics beneath that. I can, in a tongue-in-cheek sort of way, describe the difference between physics and chemistry and biology relatively simply by saying that physics, if I want to know what topics are part of physics as opposed to chemistry as opposed to biology, physics, again, somewhat tongue-in-cheek, is concerned primarily with rules, equations, rules, and in physics, none of those rules have any exceptions. There's the theory of gravity, equations that describe gravity, and everything obeys those equations, no exceptions. Chemistry, on the other hand, loves to use rules, but only rules of thumb, right? You might know periodic trends in the periodic table, but some of the elements act a little bit weird. Or you might be familiar with named reactions that work fine for most of certain class of molecules, but there's a few exceptions, right? So chemists love rules that have exceptions to them. So rules of thumb, all of which have some sort of exceptions. And then again, somewhat tongue-in-cheek, biology could be described as a whole bunch of exceptions, a whole bunch of one-off observations with relatively few rules that define them. So that's not a terribly rigorous way of defining the content of these fields, but it's a reasonably useful way of understanding the psychology, maybe, of how physicists and chemists and biologists think about things. And in that sense, this name, physical chemistry, tells us that chemistry has something to do with physics in addition to chemistry. So another way of describing what physical chemistry is physical chemists like equations, they like rules, they like them especially when they don't have terribly many exceptions to them. So it's as if physical chemists are studying the topics of chemistry, the content of chemistry, chemicals, chemical reactions, but using the principles or the models of physics to do so. So it's taking sort of a physics approach to chemistry problems. So that's yet another way of understanding what physical chemistry is. So hopefully that gives you a reasonable overview of where we're going. And the next thing we'll do is talk a little bit in more detail about these topics that we're going to cover in the physical chemistry course.